Admit all. This is not. Hmm. Okay, while class is going on, if anyone is waiting in the lobby, let me please let me know. Where is this PPT? Hmm? M. Srinivas. He's not here. He's maybe in another staff room. He shifted. Okay. Okay, guys, let's discuss about trees. Uh, so let us go with a small definition. In generally, a tree is a finite set of one or 1 second, whether my voice is audible or not. Yes, it's audible. Okay, no problem. This time, instead of installing the application, I'm directly going through this browser. That's why these many settings and these many times I'm asking. Mm, I'm coming over here. Then where is this record option? Record. You have to share more. Okay, let it be. I should record. Mm, mm. So, generally, we know the definition of the tree. A tree is a finite set of one or more nodes such that there is specifically designated a node called a root for any tree. In physical, whatever in nature, we are seeing the trees with root, branches, and leaves, right? In the same way, we are going to construct a data structure where it contains, of course, what you already learned in BE, I mean, under graduation. So, same thing here also. So it is designated with a node called root, which is having remaining nodes that is n greater than or equals to 0. So we can call them as disjoint sets like T1 to Tn, whereas each of these sets is a tree. For example, if you take T1 to Tn are called the subtrees of the subroots, depending upon the levels. If you see here we are mentioning that level 1, level 2, level 3, level 4. In level 1, there is a root. In level 2, there is another subtrees, and level 3, another more subtrees. And coming for the level 4, this is the last level where we can call them as leaves. A tree is a hierarchical data structure consisting of nodes where each node has a parent except the root and zero or more children. If you consider anyone, either B or E or K or L, every node will have a parent node except root node. And every node will have a child node except leaf nodes. Okay. So, and whenever we are discussing about types of trees, there are different types of trees like binary tree, BST, balanced trees, heap tree, TREI, segment tree, and some traversal techniques to utilize the trees. So coming for the binary tree, each node has at least at most two children. Why? Because it is a binary, either 0 or 1. And coming for the binary search tree, it contains left node, right node with a root. So always left side node will be less than the root and right side node will be greater than the root. Coming for the balanced trees, AVL trees and red back trees are known as the balanced trees, and we'll discuss about them. Coming for the heap, it is a complete binary tree used in priority queues. Depending upon the priority, if you are mentioning any queues, we can call them as heaps. And TRI, efficient for search operation, example like dictionaries. So in the dictionary is completely different when you whenever you are searching, the dictionary structure will be different. With the help of some elements, we can find whatever thing we need. Such type of tree is a TRI, segment tree, which is used in range queries. And coming for the tree traversals, if you go through there are two different types of traversals. One is DFS, another one is BFS. In DFS, we can call the full form is depth first search. So there are three different types of orders are there in DFS. One is pre-order, in order, post order. Whenever you are filling the element from root first, then left, next right element, then we can call it as pre-order and pre-order traversal. And in order, left node will be filled first, then go to the root node, finally right one. And coming for the post order, first left right, afterwards root. So here pre means root will comes earlier, post means root will come after, and in means it will be in between left and right. And whereas you come, this is about depth first search. Whenever you are discussing about depth first search, it will traverse level wise, level 1, level 2, as we seen in the earlier figure. So level 1 nodes will be filled first, then only they goes for the level 2. In such a way, if you go step by step, like operations in BST, that is in binary search tree, the operations involved here are insertion, deletion, search, minimum, and maximum. So insertion, add a node maintaining a order. In binary search tree, it contains only two equal paths, so it will maintain one order, and element will be inserted from left or right depending upon the situation. And deletion also, it will also removes a node while preserving the structure. Whereas such finds a node efficiently, as it is binary search tree, the tree will be divided into two equal parts. If our element is in the left part, right part will be ignored. If our element is in right part, left part will be ignored. Coming for min or max, leftmost is always minimum, rightmost is always maximum value will be there. So if you take any values from 0 to 99, if you divide that one into two equal parts, 50 at one side, 50 at one side, 51 to 99 will come at right side, 0 to 49 will comes at one leftmost side. So if your element is in the leftmost or rightmost, will be decided with the help of the BST. So coming for the balance trees, AVL tree, red black tree are known as balanced trees. Why AVL tree is a self-balancing using a self-balancing tree which will use rotations. Red black tree maintains balance with color rules. And coming for the applications, BST is efficient in searching. Heap will be used in priority queues. Try will be used for autocomplete, and of course IP routing. Segment tree is very fast range coverage. Of course, we'll discuss about these things in detail also. Coming for the priority queue, it is an abstract data structure where each element has a priority. Only depends upon its priority, element will be dequeued. Of course, sometimes enqueued also based on a priority rather than the order of the insertion. For example, you can say you already have some idea about operating systems. In operating systems, there are different types of searching methods are there, like shortest job first, FIFO structure, SJF, shortest job first, first come first serve, like that. What the structures will say is they will be completely depend on some order. If any search is happening depending on the priority, the prioritized element will be executed first. For example, for a processor, if any two two processes or two threads are asking for execution, processor will execute the thread or a processor or instruction depending upon its priority. Okay. So whereas coming for the heap, a heap is nothing but a specialized tree based structure that satisfy the heap property. For example, we can also implement these heaps by using binary heap or Fibonacci heap. Fibonacci is, that is the 2 into 1 into 3 into 4, like that. It's a structure. Whereas max heap, highest priority element, has the largest value, and min heap, highest priority element which is having the smallest value. For this, by using these priority keys, we can again perform operations like insertion and deletion. Whereas insertion is will be denoted with a logarithm, I mean big O of log n, whereas deletion will extract minimum or maximum value of big O of log n. And we will use another operation called peak, where we can get minimum or maximum value. Coming for the properties, implemented using complete binary trees, typically stored in an array for efficient arrays. Insertion deletion using heapify operations, that is nothing but heap operation. Heapify is the process to maintain heap property. Coming first step by step, so whatever the trees we discussed in a brief, we will discuss about those trees in deep now. Coming for the binary search tree, it is a binary tree where each node follow those properties. The left subtree of a node contains only nodes with values less than the node value. The right subtree of a node contains only node with values greater than the node's value. Means binary search tree will always contain the nodes with less value at the left side, greater value at the right side of the root. Okay. And the left and right subtrees must also be BSTs. Even if you take any subtree, whether on left side or right side, if those nodes are acting as a parent, so that nodes also must follow the same rule. That is BST rule. So binary search tree rule is whenever any node is acting as a parent, the leftmost children must be have lesser value than the root, and rightmost children will have greater value than the root node. So basic BST operations are Either insertion, start the root. I mean, we can insert the value just by starting the root, compare the value to be inserted with the current node. If it is smaller, go left. If it is larger, go right. So while doing inserting operation in BST, we will start from the root. If the value which you want to insert is less than the current node, that is root node, if it is smaller, it will go at left side, and if it is larger, it will go to the right side. Repeat until an empty spot is found. This is how binary search tree will work in insertion operation. And if you go for the search operation, start from the root. Compare the target value with the current node. For example, if the target value is 9 and if the node value is 10, definitely your value 9 will be at the left side of the root node. So in such a way, we can say if it is smaller, search the left subtree. If it is larger, search the right subtree. So the search operation in the first step itself, it is omitting 50% of the structure. So very easy to find out the value. Repeat until the value is found or leaf is reached. Until if you reach the leaf, if value is not found, means it's a null value. Coming for the deletion, there are three cases. In case one, node has no children, simply remove it. If you want to remove any node, if node has no children, you can remove that. Case two, node has one child, replace it with its child. Means whenever you are removing the node, the child will become the main node, whatever the node. So whatever the element you are going to delete, if you delete that one, who is acting as a child will be act as a node. Case 3, node has two children. If the node is having only single child, if the node has two child, replace it with in order successor, smallest value the right subtree, or in order predecessor, largest value in the left subtree. Means you must interchange the values. Smallest value will be at the in order success, like replace it with in order successor, like smallest value in the subtree, right subtree, or in order largest value in the left subtree, whatever the thing you want. So while deleting, you must keep it in mind that if node has no children, simply remove it. If node has one child, replace it with child. If node has two children, check whether it is greater than the root node or less than the root node. If it is smallest value, make it as a right subtree. If it is the largest value, make it as a left subtree. In such a way, we can do the deletion operation in binary search trees. And coming for the tree traversals in binary search tree, traversals refers to visiting all nodes in a specific order, like in order, left, root, right. Here we already briefed this one starting, but here we are going step by step. Produces a sorted order of elements in BST. Example: 1, 2, 3, 4, 5, 6, 7 is our values. In such a way, the data has to be inserted in pre-order: root first, next left, next right. Okay, used to create a copy of the tree or prefix expression evaluation. Whereas in post order, first fill the left node, then fill the right node, then last value will be filled by the other root node. Using in deleting a tree or evaluating a postfix expression, level order, that is nothing but breadth first. So uses a queue to process nodes level by level. Which level has to fill first, which level has to fill next, will be decided by the level order in the breadth first search. So, and coming for AVL trees, AVL is nothing but Adelson, Welsky, and Landis tree. It is its full form. So an AVL tree is a self-balancing binary search tree. We already know about the binary search tree where root will be at the top, minimum value will be at the left, maximum value will be at the right. And what is AVL tree means? It is a balanced, self-balancing binary search tree where height differences depending on balance factor or left and right subtrees of the node. It is the most one balance factor. The balance factor of the node is balance factor equals to height of left subtree. Balance factor equals to height of left subtree minus height of right. So whatever the height of left subtree is there, you can minus the right one. If balance factor is minus 1 comma 0 or 1, the tree is balanced. Why? Because left subtree is less than 0, minus 1. Right subtree is greater than 0, 1. So the tree is already balanced. If balance factor is less than minus 1 or greater than 1, the tree is unbalanced and required rotation. How the rotation will take place? In such a way, rotations in AVL trees, when the balance factors goes out of range minus 1 to 1, rotations are used to restore balance. Example: types of rotation. Right rotation, single, LL, we can also call as LL. Why? Because at the left side it is imbalanced. That's why we are performing right rotation. Used when left subtree is too heavy, fixes left imbalance. Rotate right around the unbalanced node so that by rotating right side, left side will be balanced. And left rotation, if it is unbalanced at the right side, we will do the left rotation. Used when right subtree is too heavy, fixes right imbalance, rotate left around unbalanced node. So left right rotation, that is nothing but LR rotation. We can also call it as double. Used when left child has a heavy right subtree, fixes left right imbalance. Perform left rotation on the left child, then right rotation on the unbalanced side. Right left rotation, this is double, means used when right child has heavy left subtree, fixes right left imbalance, perform right rotation on the right child, then left rotation on the unbalanced node. So this AV in brief, in single line, AVL is a balanced. We as we discussed, its definition is AVL tree is a balanced binary search tree. Binary search tree means always the value, the left side value of the element will be minimum value when you compare with the node. Right side value will be the maximum value when you compare with the road node. This is the binary search tree. And AVL tree is a self-balanced tree where by mistake or by the structure, if any unbalancing is there, we will use either of these right rotation or left rotation and we make the tree as a balance. If you are not making, it has to be balanced as we are using AVL trees. Okay, means for example, in Excel sheet, if you are entering values and you click on sort operation, so 198423 6 like that you are entering in a different order without following any ascending order, descending order. So here, what will happen in Excel sheet? If you keep on sort, if you click sort option in Excel sheet, it will follow the rotation and it will go through the ascending order. No, if you want descending order, it will perform another type of rotation depending upon the program structure. Okay, insertion in AVL tree, insert the node as in a regular BST. How BST will be act while insertion operation? Minimum, if you want to insert any value, if that value is minimum lesser than the value at root node, we will fill at the left side. If it is greater than the root node, we will fill at the right side. In such a way, you should follow the same rule in AVL tree also. Update the balance factor of each ancestor. Every time you must update the balanced factor. Means this root value is 0. Always minus values will be on the left side, plus values will be on the right side. This is the balance factor of that root node. In such a way, every subtree, every subroot node will have a balancing factor. If node become unbalanced, perform the required rotation. Deletion in AVL tree. Remove the node like in a regular BST. So how you are removing? Depending upon if it is three cases are there. If it is not having the child, no problem. If it is having the one child, replace with child. If it is having two child, so make it as a left subtree or right subtree. Update the balance factors of the ancestors. If any node becomes unbalanced, perform the necessary rotations. So applications of AVL trees. We will use these AVL trees in databases and indexing for fast searching. Best example is like say, uh, in the database, data will be stored in the form of a record. So for our understanding, I am saying one example as a Microsoft Excel. Okay, memory management, OS page replacement algorithm. So you people already know about replacement algorithm, like paging in computer organization architecture in the memory management, which is a fifth unit in BTech. Okay, memory management. And next are file system organization. Whenever if you want to organize all file systems in a particular level, then we will use this AVL trace. Routing tables in networking. In networking, routing is nothing but a process of routing the packets from source to the destination. These routing tables, what they will do is, while sending the packet from source to the destination, the packets will choose their own way. But at the destination, they has to arrange in an order. This order will be maintained by using this AVL data structure. Okay, AVL tree. Next, coming for the split tree. We can also call this one as self-adjusting binary search tree. So, a split tree is a self-adjusting binary search tree that performs a split operation. So earlier, AVL tree will perform rotate operation. Here we will perform split operation. Both will use the binary search tree structure, but both and also both are self-adjusting trees only. After every access to move the access node to the root, this improves access time for frequently used nodes. Generally, what are split tree operations? Split operation means it will move a node to the root. It will move a node to the root using rotations based on its positions in the tree. There are three cases. Case 1, jig, that is nothing but single rotation. Case 2, zigzag, double rotation in same direction. Case 3, zigzag, double rotation in opposite direction. In such a way, this play operation, whatever the element you are inserting, first it will move that element to the root, and there it will search whether this node is greater than the root node or less than the root node. Depending upon that, it will perform either jig operation, jig operation, or zigzag operation to make it as a complete binary search tree and to make it as balanced. Okay, insertion in split tree. How insertion will be done? Just like BST means binary search tree. Splay the inserted node to the root node. Search in split tree. Perform a standard BST search. That is nothing but whenever if you want to search any element, first of all you will go to the root node, and if the element is lesser than the root node value, then you will search at the left side. If the element is greater than the root node value, you will search on the right side. So split the found node to the root. So our last access node if not found. So how we will delete in split tree? Same like BST, but split the node to be deleted to the root. First move that node to the root, then remove that root node. You can't remove as a leaf node. Split the tree into left and right subtrees after deletion. So after deleting the root node, you can divide the left subtree and right subtree. Split the largest node in the left subtree to make it a new root. Okay, so in the left side, whatever the largest value is there, you can make it as a new root. Then what happens? If you go to the right subtree, minimum value node will be the root. Why? Because all right side values must be less than the root node. If you are taking at the left side, maximum value of left subtree, maximum valued left subtree node will be the root. Then what happens? On the left side, all values of the element will be less than the root node, and at the right side, by default, it will be greater than the root node. Again, it is forming a very good binary search tree. Okay, attach the right subtree. Applications of split trees: caching systems, where LRU cache, memory management, data compression, move to front heuristic. So network routing algorithms, all these are the applications of split trees. Okay, next coming for the skip list. You people know about the list. Skip list is with a different element. A skip list is a data structure that allows for efficient search, insertion, and deletion of the elements in a sorted list. It is probabilistic data structure, meaning that its average time complexity is determined through a probabilistic analysis. Means it's just like a flipping the coin, and 50 what will be the value, you can predict by the probability. 50% chances are for tail, 50% chances are for the head. So in such a way, skip list is one of the data structure where we will follow the to find the average time complexity, we will follow the probabilistic analysis. In a skip list, elements are organized in layers, with each layer having a small number of elements that one below it. The bottom layer is a regular linked list, while the layers above in contain skipping links that allow for fast navigation to the elements that are far apart in the bottom layer. The idea behind this is to allow for quick traversal to the desired element, reducing the average number of steps needed to reach it. Okay, and skip lists are implemented using a technique called coin flipping, just like prediction. In this technique, a random number is generated for each insertion to determine the number of layers the new element will occupy. This means that on average, each element will be log n layers, where n is the number of elements in the bottom layer. So, skip lists provide a simple and efficient alternative to balanced trees for certain use cases, particularly when the average number of elements in the list is large. So, if average number of in the list are large, you must skip. How can you skip? Just by predicting, by following the probabilistic analysis. In another way, if you take the binary search tree, if the value you are searching, if the element you are searching is less than the root node, you will search at the left side. If it is greater than the root node, you will search at the right side. In such a way, skip list will, with the help of the probabilistic analysis, simply they will go either this side or that side. Okay. Advantages of skip list is the skip list is solid and trustworthy. And to add a new node to it, it will be inserted extremely quickly, easy to implement compared to the hash table and binary search tree. The number of nodes in a skip list increases and the possibility of the worst case decreases. Requires only login time in the average keys for all operations. Finding a node in the list is relatively straightforward, but some disadvantages are also there. Why? Because it needs greater amount of memory than the balance tree. Reverse search is not permitted. Why? Because we are skipping the list so that we don't know the root node or parent node for each leaf. That's why reverse search is not permitted. Means undo can do, but redo cannot do. Searching is slower than a linked list. Skip lists are not cache friendly because they don't optimize the locality of the reference. Okay, and this is about unit 1. As of now, we completed first unit and where it is completely containing the um, data structures. Admit all. Why by this Thakur is still waiting? Huh?